Take a look at some examples with some rather unusual exponents. So, in number 11, m to the 2n power minus 16. Well, anything that has an even exponent is a perfect square. And if you multiply any number by 2, you're going to have an even exponent. So, since m to the 2n power is a perfect square, and 16 is a perfect square, we have a difference of squares. Well, if I take the square root of my first term, m to the 2n power, well, this is the same as m to the 2n power raised to the 1/2 power. When I raise a power to a power, I multiply the exponents. So this becomes m to the 2n times 1/2. Well, that's just m to the n. And then the square root of my second term is 4. So this factors into m to the nth power plus 4 and m to the nth power minus 4. In 12, just like with perfect squares, anything to an even power is a perfect square. Well, anything that has a power that's a multiple of 3 is a perfect cube. So x to the 3n power and y to the 6n power are both perfect cubes. So I have the cube root of x to the 3n power, which is the same as x to the 3n power raised to the 1/3 power. So that's x to the nth power. And the cube root of y to the 6n power is the same as y to the 6n power raised to the 1/3 power. So that's y to the 2n power. So this factors into x to the nth power, y to the 2n power, times x to the nth power squared. So this is x to the nth power squared, which is x to the 2n power, y to the 2n power squared, which is y to the 4n power, and in the middle, I multiply x to the nth power times y to the 2nth power. This is SOAP. So this is the same sign, the opposite sign, and always positive. So again, in 13, the same as number 12, 3p and 12p are multiples of 3. So that makes this a sum of perfect cubes. So when I take the cube root of a to the 3p power, well, that's just a to the p power. And the cube root of b to the 12p power is b to the 4p power. When I square a to the p, that's going to give me a to the 2p power. When I square b to the 4p, that's going to give me b to the 8p power. So my pattern is the cube root of my first term, a to the p, the cube root of my second term, b to the 4p, times my cube root squared, a to the 2p, my cube root squared, b to the 8p. In the middle are my two cube roots multiplied, so a to the p times b to the 4p. And my signs are the same, opposite, always positive. Number 14 looks scary, but it isn't. I don't want this y to the negative third. That makes it very complicated to multiply. So since I don't want it, I'm going to make it go away. Anything that I want to make go away, I'm just going to factor out. And between 48, 32, and 80, I have a 16 in common. I'm going to divide everything by 16y to the negative third. So I have 48 divided by 16 is 3. Y to the negative third divided by y to the negative third is 1. 32 divided by 16 is 2. Y to the first over y to the negative third. So this is y to the first over y to the negative third. That's 1 minus negative 3. So it's y to the fourth. Minus 80 divided by 16 is 5. Now I have y squared divided by y to the negative third. Well, this is 2 minus negative 3, so that's y to the fifth. And I can't do anything else with that. Okay? In order to use quadratic form, my exponents have to be even, and one has to be half than the other. And 5 is not even, it's odd, and 4 is definitely not half of 5. So this is my final answer. In number 15, I'm going to factor out 2 because they have a 2 in common. And then when all of your variables are the same, remember you're supposed to use the variable with the smallest exponent. Well, in this case, since my exponents are negative, my smallest exponent is negative 5. So 16 divided by 2 is 8. B to the negative fifth over B to the negative fifth is just 1. Plus 20 divided by 2 is 10. And this will be negative 4 minus negative 5. So that's negative 4 plus 5. So that's just B minus 6 divided by 2 is 3. And this will be negative 2 minus negative 5. Well, that's negative 2 plus 5. So this is B cubed. And the only other thing that I can do at this point is I can say 2 times 8 plus 10b minus 3b cubed over b to the fifth.